Okay, I believe this is recording. Okay, so welcome everyone to today's edition of Batch Working Group. Today is 21st July, and I'm Swati. I'm going to be moderating today's meeting. Just a quick reminder before we go into the agenda that this meeting is recorded, and please be mindful of CNCF code of conduct. With that out of the way, we have Albin today, who's going to be giving an overview on Armada. Welcome to the group, Albin. Over to you.
Thank you. Let me share my screen. It says that host has disabled participant screen sharing.
I think you should have co-host now.
Yes, thank you. Can everyone see my screen now? We can give a thumbs up. Awesome. Right. So today's presentation, I'll be giving an overview of the Armada project, which is something that we're working on at GR-OSS. And the project is open source, and you have the GitHub link here at the slides. So first, a bit of an intro. So my name is Albin Severinson, and I work for GR-OSS, which is a fintech company based in London. We recently also have an office in Dallas, and in addition to that, a couple of open source developers scattered across the world. And we build and operate a large research platform for quantitative researchers. Essentially, these people look for patterns in large real-world financial and market data sets, typically very noisy data sets. And so these researchers, in addition to, well, so I can also mention that GR has been around for something like 20 years at this point. And over the years, we've had an increasing amount of on-prem compute that we wish to utilize efficiently. And so these researchers and automated systems run large number of batch jobs. Primarily, these batch jobs are for machine learning and AI type workloads. Historically, many of these have been running on HTC Condor on Windows, and we are now in the process of porting them to Kubernetes on Linux. So for this reason, we need a queue or scheduler to which these batch jobs can be submitted to be run somewhere in our estate. And so our target for such a system is to manage on the order of 100,000 nodes, something like 1 million cores and a large number of GPUs and other accelerators. In addition, for the system, we need to handle submitting on the order of tens of thousands of jobs over a short span, where such that they can be queued, and then over a longer period of time, they can be sort of drip fed into the underlying compute resources to be run. We also need to handle scheduling jobs of varying shapes and size, from single core to multi-node jobs. We need to divide resources fairly between users, and we need to provide detailed visibility for users and admins. Right, so this is what we want at sort of a high level. So let's talk a bit about what options we have for achieving this. Right, so the easiest and the thing that should be considered first is whether we can use Kubernetes with some existing scheduler, whether that's Volcano or Q or the vanilla scheduler with some sort of plugins. So let's do some back of the envelope calculations for what we need. So for 1 million cores, and if you have 1 million cores, in the limit, we would have 1 job per core, and say that they last on average 10 minutes each. At that point, in order to keep the cluster filled, we would need to schedule up to about 1,700 pods per second, and that's a lot of pods. And in addition, to avoid submit queries timing out, we need to ingest on the order of tens of thousands of jobs in single-digit seconds. So there's a couple of concerns associated with running at this scale in Kubernetes. So first of all, having more than, say, 10,000 nodes in a single Kubernetes cluster is tricky. I think the official limit is 5,000 nodes, although, for example, the OpenAI people have managed to push that to 7,500 nodes. Perhaps you could push that further, but if you start going to, say, 4 times or 8 times the scale of what the OpenAI people, things might become really difficult. In addition, it might not be something that you actually want to do. For example, if you have a single Kubernetes cluster and you roll out a bad config change, you might actually take down your entire compute. So that's one of our concerns. Another concern is that existing systems such as Volcano or Q, typically based on etcd, which in our experience, so HCD provides good durability and consistency guarantees, but in our experience, it's difficult to scale the performance of HCD, particularly throughput, to the scale that we need. At the same time, we don't want to build something entirely custom to replace sort of the existing thing either. We want to leverage the work that's going on in the community. So that leads us to the high-level solution that we've chosen, which is to build something on top of several Kubernetes clusters. The idea is to have some higher level system that manages several underlying Kubernetes clusters. In particular, we wish to have something that can schedule jobs across many K8s clusters, such that we can scale beyond the capacity of a single cluster. And we want to move part of the queuing and scheduling logic to something outside the cluster, perhaps something that has weaker consistency guarantees in order to improve performance. The advantages of such an approach is that we can improve throughput and reliability, right? So we can take down a cluster for maintenance transparently to the users, for example. We can also do things like having canary, experimental, and specialized clusters. Perhaps we can have a couple of on-prem clusters and a couple of clusters in the clouds. So the disadvantages of such approach is that at this point, we block direct access to the underlying clusters. The things that you want to do on the underlying clusters have to somehow either be supported by the high level system or be passed through to the underlying system by the high level. Finally, it's also the notion of all problems can be solved through additional layers of abstraction, except for the problem of having too many layers of abstraction. Right? In doing this, we're adding complexity in some sense. And our implementation of such a solution is called Armada. Armada is an eventually consistent meta scheduler for Kubernetes. Users submit jobs to a central service, which we call the Armada server. These jobs are then leased by the server to executors, each of which lives in its own separate Kubernetes worker cluster, which submits them to the in-cluster scheduler in the respective clusters. And that could be, say, the vanilla scheduler or Volcano. Armada takes exclusive control over all of these worker clusters. Armada has been in production at G-Research for over a year and is actively developed by about 10 people. So here we have a schematic overview of how the system works, how the system looks like. Each of the blue boxes is a separate Kubernetes cluster. One of them is running the Armada server. It keeps sort of some internal state there, and the users interact with the Armada server. Then you have some number of Kubernetes worker clusters, each of which has running inside of it an Armada executor. The executor talks to the Armada server and then sort of propagates whatever the server wants to do down to the underlying Kubernetes cluster. In particular, it submits pods to the scheduler inside of it, each worker cluster. And then it sort of does things like monitoring how those pods are doing and reporting back and things like this. So for Armada, the core concepts that we're interested in is that of a job, which for us means a bag of Kubernetes resources. For example, a pod spec plus an ingress to be created, plus some Armada specific metadata. So when you submit the job, and we'll get into a bit more detail on this in a minute. Typically what you say is, I want to have this pod, I want it to run somewhere, and together with the pod, I want to create some additional resources. We have job sets, which is an implicit grouping of jobs that can be managed as a unit. And we have queues, which represents a user or project, and which is the basis of how the system divides resources fairly. Users submit jobs to these queues via a gRPC API. Each job has a priority that determines its in-queue order, and each queue has a weight to determine its fair share. So a server, sort of the meta scheduler, then multiplexes between queues, the different queues, to pull out jobs to give to the executives. Users then subscribe to events, things like running, failed, finished, etc., associated with the jobs in a particular job set. There's more details on this as well in our docs. On the architecture side, Armada consists of a set of loosely coupled services that are connected via a log-based message broker. So a log-based message broker is essentially, it's a system like, we use Pulsar. Another example is Kafka. It's a system, it's essentially a message bus that consists of some number of topics to which you can submit messages and to which downstream services can subscribe to receive all messages submitted on a particular topic. So what happens when a user submits a job is that you connect to a submit API endpoint. That translates into a message that gets put onto some topic on Pulsar. Other components, such as the scheduler, then subscribe to these messages. So whenever a message is received, whenever a job is submitted, a message is put on the Pulsar, which is then eventually handed off to the scheduler, which writes something to its internal state. Scheduler then creates sort of these job leases, these decisions to give a job to a executor, and it puts a new message onto the message bus on the Pulsar. That allows other downstream systems to consume that message and then update internal state. So in this way, Armada is eventually consistent, since each of these downstream components may have read a different number of messages on any given topic. You may be familiar with this design pattern of event sourcing. There are further details on the state messages that you support on the link at the bottom of the slide. So that's essentially it on the architecture side. Next, I'll talk a bit about using Armada. So we discussed submitting jobs to Armada, and this is what a so-called job spec looks like. It's essentially a Kubernetes pod spec. So here you can put anything that is a sort of a legal Kubernetes pod spec, you can put into here, and these things are essentially propagated down transparently to the underlying Kubernetes cluster where the job is scheduled to run. In addition to that, we put some Armada-specific metadata, such as the queue you want the job to be submitted to, the label of the job set ID, the priority, and a few other things. Our intention is to keep this as transparent as possible. We don't really want to have too much Armada specific. We want to pass as much as we can down to the underlying clusters. You can, once you have one of these specifications, you can submit them using the Armada CTL command line utility, which internally communicates via the gRPC API. Armada CTL also allows you to watch for updates on the jobs that you submit. For example, here we have an example where you submit 2 jobs. Eventually, these jobs transition into the leased state, meaning that they'll be given to an executor. Pending, meaning that they're about to be created in the underlying cluster. Running, meaning that we started them and then succeeded once they run to completion. Internally, we also have specialized tools such as workload managers that submit and monitor jobs directly via the Armada API. We have clients available for Go, .NET, and Python. And we are also working on the first-party Airflow integration. Further, for monitoring submitted jobs, we have a React web UI that is called Lookout, which shows stats and info for queues, jobs, and job sets, allows for canceling jobs and job sets, and supports viewing job logs. In addition to that, you can also, if you wish to, write sort of bespoke interfaces that subscribe to job updates to populate whatever interface it is that you want. That's essentially for the state Armada is at now at a high level. In addition to these things, we have a large number of items on our roadmap for this and the coming year. So this includes first-class distributed jobs, smarter scheduling, including gang scheduling, preemption, bin packing, topology awareness, and urgency. Job elasticity, meaning having distributed jobs that are composed of some number of pods that may change throughout the lifetime of the job. We're also working on improved observability for users and admins and open source tool integration, such as for Airflow. Further, we are now in the process of making 2 important technical decisions on where we want to be aligned with what happens in the community. So this is something where we would like the input of the batch working group. In particular, we are deciding on the representation of distributed jobs and which in-cluster scheduler to use. Today, we're using the vanilla scheduler. In the future, we may continue using the vanilla scheduler, perhaps with some set of plugins, or we may switch to using something like Volcano to support some of the features on the roadmap. In particular, I want to speak a bit about distributed jobs and what that means for us. So to us, distributed jobs, what we want to represent, It's a job that consists of one or more coordinator pods, one or more pools of worker pods that may be scaled up and down dynamically, a set of auxiliary services, maybe a SQL server to record metrics throughout the lifetime of job, and some number of additional objects such as services. Our current thinking, which is inspired by, I think it's a proposal put forward by this batch working group, is to model these distributed jobs by a collection of pod groups, each of which is a collection of identical pods with a min and max number of pods. Where you start a job where you have the minimum number and you can sort of dynamically go up to the maximum throughout the lifetime of the job. And one of the open questions on this is then is, or should also mention, is that really clear how to, one of the things that is still not clear is how to manage combinations of long-running services and workers, where you may have higher uptime guarantees for the long-running services than for the workers. More details on our current design thinking on this and the 2 PRs that are linked at the bottom of the slide. And finally, you can try this out. There's a quick start on our GitHub, which allows you to deploy a minimal Armada environment locally, submit jobs to it, and view some metrics. Should be noted that Armada works, and it works really well for us, but there are some sharp corners, in particular around the number of components required to operate a Armada cluster. That said, if you run into issues looking into this, please, you can just drop me an email and I'm sure we can set up a call to help you figure it out. And that's it from my side. So my name has been Albin and research. This is my email in case you want to contact me on anything. The Armada GitHub link is linked at the bottom, and sort of the standard shout that if you're interested in things like this, we are hiring. And if you're interested in that, you can also just drop me an email at chat. And with that, I'd like to open for questions.
So if I may, yeah, if I understand correctly, your major feature request for the Kubernetes vanilla scheduler is all or nothing. Is that correct, or are there more requirements?
Yeah, we essentially want all or nothing scheduling of some number of pods. And in addition to that, we want some sort of custom resource definition that is sort of commonly understood by schedulers. From what I can see, there are at least a couple of different sort of proposals for pod groups and jobs that are floating around. For example, Volcano have their own pod group and job definition. So ideally, this would be standardized by the community, and we would support whatever is the standard in the community, as opposed to having a couple of different standards used by different projects.
Yes, that's an active discussion for pod group, this pod reservation. So I suggest you keep yourselves in the loop of those discussions, and if you can even comment on the CAP, I think that would be very useful for us.
Is this the one that is in the batch working group email list?
Well, some of those conversations trickle down to the respective SIGs. So this one in particular has been discussing the SIG scheduling. But I mean, you can look at it in the enhancements repo.
Yeah. Do you have any other questions on this?
I see Maciek has his hand raised. Do you want to go ahead?
Yeah, so maybe I can ask. I would have a few actually. Maybe starting from one comment on the question that you had regarding the choice of scheduler. One, watch out from like a cloud provider's perspective that any custom scheduler implementations cause lots of problems with auto-scaling in cloud, which then means that all of these registrators of jobs that customize scheduling decisions they struggle with adoption in cloud context. So things like Volcano, they get little traction, or if they get, they result in lots of problems for users because cluster autoscaler needs to run scheduling simulations to make decisions, and we frequently see conflicting decisions made by a custom scheduler and the cluster autoscaler. So if ideally, if I can just throw a recommendation in here, at least from cloud providers' perspective, that it would be best if you made the decision like as a plugin or in some way open to the end user, so they can decide which scheduler they would like to use. Because especially in cloud, moving away from the vanilla scheduler that the provider offers as part of EKS, GKE, or other service would just work best with autoscalers. And aside from that comment, I had a few questions. One or maybe two, if in a combo. So would, in this architecture that you have, would it be possible to have multiple Armada servers that manage the same set of clusters? And also, in your architecture, is it possible to have also workloads not managed by Armada running inside those clusters?
So on the first question, it's like you can do both of these things. And the only problem that you're going to run into is that you're going to have conflicts between them, because the executors will tell the central Armada server how much capacity they have. And the central server will use that in making its scheduling decisions. So if the amount of resources available changes significantly between the time the executor tells the server and the server then giving the executor a job, the job would then be returned to the server to be reattempted scheduling. So you can totally do it, but you're going to introduce conflicts between the schedulers.
So you may have essentially race conditions, right, in these scenarios then? Coming from like two servers trying to submit jobs and then fighting for capacity. Okay.
Yeah, they're fights.
Okay. And then in terms of workloads that run outside, I assume then it's the same problem, right? That something could steal capacity that is available, and Armada server could send a workload to a cluster, and then something else in the meantime would steal that capacity.
Yeah, that's exactly correct.
Okay. And just one thing, the way you measure available capacity, you look at like what's allocatable in the cluster, or there is some form of like custom resource that defines what's the maximum capacity available in a cluster?
No, it just looks at the nodes available and what they're currently running.
Nodes available. Okay. So then it would also require work to make it to operationalize it with autoscaling, right?
That's correct, yeah.
Okay.
I see.
Diana, you have your hand up. Diana, do you want to ask a question?
Yes. Great. Thank you, Albin, for your presentation. A couple of questions just to follow up on this last question that you answered. When you determine on the target clusters where the workloads are going to be dispatched to, do you also consider things such as taints and tolerations?
Yes, we do.
And allocation restrictions? Great. Okay.
Correct. We use all of this. Essentially, we do all of the things that the underlying scheduler would consider.
Okay, got you. And the other thing is, so you talked a bit about the enhancements at representing the jobs that you would like to see. And then if I'm understanding correctly, the limitations as far as the current Kubernetes system is that the throughput, right? It sounds like the issue of being able to do the amount of throughput that you want may not be able to support it because of the limitations of etcd. Is that correct?
Yeah, so that has been our concern and our experience.
Okay. Got it.
I think the problem is essentially fundamental to the design of etcd, no, in the sense that you pass everything through a single point in order to provide the consistency.
Right. Is there any other things that would limit that if that problem was resolved? Is there anything else?
So there are other things that sort of limit how big you can make your clusters, such as sort of how easy you can, things like the overlay network, for example, can also make it difficult to make these clusters very, very large.
Right, that's correct. So, and that's why you use multiple clusters. But my question more was being able to have still using multiple clusters, but having one cluster doing the dispatching, but more in kube native objects as opposed to a higher level control plane, I guess is the right way to think about it.
Would you be referring to something like a federated approach?
Yeah.
Yeah, so we are somewhat concerned about the federated approach, and I think etcd is the main concern, essentially, that by not using etcd, we sort of enlarge our design space. We can sort of play with the consistency and durability guarantees that we are comfortable with in order to achieve the performance that we want.
Got it. Okay, great. Thank you.
All right, Aldo, you have your hand up. You want to ask a question?
Yes, two actually. So one is, what is the database you're using that provides you these guarantees?
So the system is mainly based around Pulsar, and Pulsar provides like pretty good durability guarantees. And the way that you sort of scale the performance of a Pulsar instance is through having a large number of topics. So Pulsar has sort of a storage layer and what we call a broker layer, essentially a message passing layer. And each broker is responsible for one topic. And so by having a large number of parallel topics, we have, I think in production, we run something like 100 parallel topics. You can have up to 100 nodes that share the state of your system, which means that you can scale to very high throughput. In addition to that, we're using Postgres, which if you're clever with your Postgres insertion logic, use things like the copy protocol and batched inserts, you can actually reach something like at least tens of thousands of messages written per second. And we also use Redis for some of the caching functionality in Armada.
My other question was, I think I saw you were using a custom CRD for defining your jobs. Is that because of limitations in the job API, or?
So we actually aren't. So the thing that is given to Kubernetes is just a plain vanilla pod spec. The additional metadata is sort of stripped by the Armada layer before it is given to Kubernetes. We need the additional metadata on top because we want to control which queue things are given to and things like this. Perhaps if the jobs API was enriched, we could just operate straight on the jobs API and do things like, if you can put things like queue and priority in the jobs specs. But I think for the foreseeable future, we'll need some amount of Armada specific metadata associated with the job.
Yes, and I missed if you currently have support for multiple pods per job, or is it single pod?
So far, we only support single pods per job.
Okay.
But yeah,
And,
like sorry, go ahead.
Yeah, one more question. If still, are there any other hands? No. So, if I understand correctly, you said that you are basically running the scheduler code also in the Armada scheduler to predict how much, to predict if a pod would fit in a given cluster.
Yeah, so it's essentially a two-stage scheduling approach where the Armada level scheduler is responsible for deciding which executor cluster is supposed to be given a job. And then the in-cluster scheduler is responsible for assigning that to a node. And so in order to improve the efficiency of this process, the top level Armada scheduler, it looks into each of the clusters to figure out if a job could potentially be run within a cluster. So it doesn't need to get this decision perfectly right, but there needs to be some amount of correlation for this process to be efficient. Once underlying Kubernetes class is given a job, it will try to run it. And if it can't, it will give it back to the server and the server will try again.
Sounds like you could benefit of the concept of pod reservation.
Yeah, that's likely. That will probably be, that sounds like it will be the case. That would also help us for things like gang scheduling, I believe.
Right. Okay, thanks.
Do you have any more questions?
It looks like we don't. Thank you, Albin, for the presentation. We are giving everyone about 30 minutes back. See you all in 2 weeks. Bye.
Thanks, everyone. Bye.
Thank you.
I would like to reiterate on, getting involved with the existing discussions. So please reach out to us in SIG scheduling or join the conversations in the enhancements. Or feel free to ping me in Slack, so we can keep this conversation going.
You have a somewhat complicated last name.
Yeah, I'll connect us all, Albin, Aldo. Yeah, this is Alex speaking without a face right now. Sorry. Hey, Aldo. It's early here. You don't want to see me yet.
Yeah, we'll get involved. We are very curious about what direction the community is taking on this, because we are quite keen on making a decision on this, and for that decision to be aligned with what the community is doing.
Thank you.
Thank you. And
Thank you.
as always, if you have any more questions, just feel free to email me.
Thanks,
Right.
everyone. Thanks, Albin.
Take care.
Bye.
Cool.
Thank you.
Thanks.